All right. Howdy. Good morning, y'all. Thank y'all for being here. Happy Tuesday. Hope y'all are all doing well. Um, we are in the home stretch. We've basically just got 2 more weeks, two regular classes this week, and then next week we'll have our review on Tuesday and then our final on Thursday. So classes coming up fast. I'm going to talk about the schedule and everything as we get into stuff. I was gonna have us start with a quick quiz though. So if y'all wouldn't mind clearing stuff off your desk, all you would need is like something to write with for this one. And this is just gonna cover what we talked about in class last time. So yeah, if y'all could clear stuff, and then I will pass these out. As usual, keep these face down until everyone's got one, please. Y'all are good to begin. Good luck. Let me know if you have any questions about like the wordings of any of those problems. Take about another 30 seconds if you're still working. Make sure you got your name on there. Alrighty, that's the end of time. If y'all would please pass those forward. All right. Hopefully that one wasn't too bad. Um, My feeling was that that one was going to be good for very similar to what we talked about last time. Also, kind of related to some of the homework questions that we had over, like for example, if we did that homework that had the burnup problem, then hopefully after seeing the equation in class, after doing that equation on the homework, we are familiar with those terms. Um, today we're going to talk about the last part of chapter 8, which is about the buildup of xenon in our reactor. Um, so that'll basically be the thing that we cover today. That'll finish up chapter 8. Chapter 9 is called Nuclear Reactor Analysis, and that's basically like a simulation of all of the stuff that we've done so far, talking about like the current state of the nuclear power industry, the factors that are driving the use of nuclear power, some of like the things that I think we should know in terms of like, once you go out into the world as nuclear engineers, you tell somebody you study nuclear engineering, they're going to ask you a lot of like there's gonna be common questions that come up, and so I want to talk about some of those things, like what do we do with the waste, and um, what's going on with all the data centers, how is nuclear power growing, and things like that. So that'll be kind of what we talk about on Thursday to kind of tidy everything up. And I guess this slide shows the end of semester calendar. So today's Tuesday, finishing chapter 8. We have that homework 7 that's due tonight at midnight. And after what we talk about today, we'll cover the Xenon stuff, which would be the last things that you would need to finish up homework 7. Um, Lecture 16, that's what we're going to cover that was what I was talking about, we're going to cover on Thursday. Um, the 5th is the day that I'm going to have us do a review. Um, I am going to talk about the review materials that I've already posted. If you think about what we've covered so far and how like long Dr. Svedkov's notes are, it's like 500 or 600 pages. And so I feel like if I were to try to review that by like going chapter by chapter, highlighting everything that we did, I might not even be able to get through all of it in an hour and 50 minutes because we covered so much. So my feeling is that I'm going to post the review for y'all today. Y'all will have basically a week to be reviewing and preparing. My intention for that review help session is that that's basically going to be a Q&A slash like we have those homework help sessions on Friday, but we're not going to have one of those before that week of the final exam because the final exam is on Thursday. So my intent for that Tuesday class before the final is that it's basically like a help session. Y'all will come in with questions that you have based on the homework, based on the exam review, based on maybe the reactor design problem if you're still working on that. So that's the intention for that Tuesday class. It's going to be student focused so that if there's anything that y'all are wondering about, we can get your specific questions answered versus me just regurgitating what we've already talked about. And I don't want to waste your time because we've already covered everything once we get to the final review, and all of the lectures are recorded too. So it's like if you missed something, if you wanted to see more about a particular lecture, it's all there for you. So that's the intent for that Tuesday lecture. And um, so yeah, in terms of that day, that's the 5th. That's the last day that I'm gonna accept any. So I have that homework policy set up where technically you can turn anything in, any late homeworks for like 70% as a maximum. So if you're still trying to turn in homework assignments for partial credit, the 5th would be the last day to do that. And also that's the day that the reactor design problem is due. I'm going to send an email about the reactor design problem. Basically, I'm going to make that be an extra credit assignment instead of it being a required assignment. So, and the way that those points are going to work is that it will either add some points to your lowest exam score, or it will add some points to your overall quiz grade, depending on what will help you the most. If you look at how I set up the weights for the syllabus, that reactor design problem was set to be about 10% of the total course grade. So as an extra credit, it will basically add 10 points to one exam. So like that score, if the score is out of 100 and you get 100% on it, that would correspond to 10 points. If you got a 50 on it, that would correspond to 5 points. So it could add some points to a low exam score, or it could add up to 10% to your quiz grade. So in that sense, it doesn't end up having the same effect that it would have as an assignment by itself. But if you've already worked on it, or if you were intending to do it, then it can like help you without hurting you, if that makes sense. So that's the plan for the reactor design problem. And again, if you have questions about the reactor design problem this Friday or next Tuesday, I'd be happy to answer questions about that then. And then the 7th is going to be our final exam. Question? Yeah, so in terms of the final, it's actually slightly offset by 30 minutes. So the final exam schedule is based on the university. And so because of when our class time, I could pull, actually, this is something to know just in case like you don't know how to find your final. If you do TAMU final exam schedule, um, it'll show for every semester. So like right now we're in summer 25 and it's the 10-week session. And so then this table will come up and it'll basically say, when does your class meet? This is when your exam is. So notice our class meets in this window from 10 to 12 on Tuesday, Thursday. So therefore our final exam is going to be from 10:30 to 12:30 on August the 7th. So that's this date and this time, and it's in this room. Um, you're familiar with my exam so far, so the final exam won't look really any different than the exams that you've already seen. Same structure, same closed book, closed notes, no calculator. The formula sheet will be provided. I am going to update it to cover the things we've done since exam 2. I'll be posting that soon, like either today or by Thursday. Question, Abube? I'm still working on them. I have students that are I have 2 students that need to make up the exam that are doing that today. So I'm basically going to be grading their exams and the rest of y'all's exams this week. I'll be having those if Thursday would be optimistic, Tuesday would be the latest. Question? Yeah, so what I'm gonna in Canvas I've been tracking all of the grades, and so that's where I'll get your percentages, like what percentage did you get on the quizzes and on the homeworks and yada yada. And then based on those percentages, I will export all of that and I'll do the calculations to figure out what weights are going to maximize your grade. So yeah, I'll figure out the weights, I'll calculate your grade such that your score is maximized based on the ranges of the weights given in the syllabus. Anne, you had your question? Every person's will be different. Yeah, every person will have different weights based on how, like, because somebody might do better on their exam, somebody might do better on their homework. So it's for each student. Was that your question? Okay, cool. Yeah, and then so the exam's going to be cumulative. It's going to cover everything that we've done. So like in terms of exam 1 and exam 2, we've already seen that review topic. We've already seen those reviews and seen that material. So hopefully if we reviewed those thoroughly, we won't have to spend as much time like re-reviewing that. But it's also going to cover everything we've done since exam 2. So there will be some focus on like the things from chapter 8 that we're finishing today. Also just some conceptual questions from what we talk about next time. So hopefully from seeing like the class so far, we see that what are the things to focus on would probably be like the homework problems. My feeling is that if you understand the homework, then there's not really going to be anything I could surprise you on the exam. So focus on the homeworks, focus on the quizzes too. Question, Tyler? So it's basically, yeah, so let me pull up there's a review document that's posted in the Google Drive. And so in that review document, in our drive under exam materials, final exam guide. Um, and so basically, like I said, it's a cumulative exam. So the first chapters 0 through 7. Oh, and I forgot to add 9 on here, but technically not 9 should be a part of this main topics. But yeah, basically exams 1 and 2 covered chapters 1 through 7. So all of the same derivations for those exams would hold. And that's basically what this goes through is essentially all that I did was I kind of copy pasted the contents from exam 1 review, and then I copy pasted the contents from exam 2 review, and then I added some stuff. So this would look very familiar if we had seen the other 2 reviews. And then the new stuff that we've covered would have been since yeah, anything after exam 2, which is chapters 8 and 9. And so I gave a list on kind of what to focus on, what are some like possible things and models to be aware of. Um, so like in terms of any new derivations from chapter 8, it's basically going to be the stuff that you've done on the current on homework 7, things involving like setting up those destruction equations, maybe solving parts of those production destruction equations, um, and I think things of that nature. Um, You can come back to it if yeah. Yeah, hopefully, I think by Tuesday. I'm sorry I can't get it back sooner, but yeah. If I'll try to get them by Thursday, but I'm currently moving this week, so on top of my normal stuff, I have a lot of other things. So that's not your problem, but yeah, that's why it might take a bit. It might take till Thursday. Or sorry, till next Tuesday. Yeah. Tuesday is the last day of class. Mhm, mhm. Um, And then in terms of chapter 9, that's going to be one lecture. So anything I ask you about chapter 9 will just be conceptual questions from that lecture. And hopefully chapter 9 probably won't be that much new stuff. It's mostly just like taking what we've learned in the class and putting in the context of the current like state of the nuclear power reactor industry. Yeah. Probably are instance, but the exam is during normal class now. It's from 10, so if it's from 10:30 to 12:30. So it's just 30 minutes later. So if you're here at 10 and you're wondering where is everybody, it's because it starts at 10:30. So yeah, that's there for you. I'll let y'all know when I post that formula sheet so that y'all can be looking at that too. The stuff from the first two exams isn't going to change, so that formula sheet will basically just have some things added to it based on, excuse me, based on what we've talked about in chapter 8. So I wanted to review the things that like the main ideas from last time. This will also help us probably answer or confirm our quiz questions. And then that'll set the stage for what we're talking about today, which is Xenon buildup. So last time we were talking about production destruction equations. We were talking about the formation of different fission products. Last time we focused on samarium. And there were also a couple concepts that were kind of baked into that lecture. One of them was this concept of fuel burnup. And basically, the basic idea is that when fuel like uranium goes into the reactor and it fissions, those uranium atoms disappear, they get depleted as they fission, and fission products get formed. So the fuel, like the heavy metal atoms of uranium in our fuel, they disappear from our fuel, they get burned up, or we might say they get depleted. And the burn up is a quantity that we use to basically describe how much energy did we extract from the fuel that we put in our reactor. So the common units for it would be megawatt days per kilograms of heavy metal or an atom percent. If we're talking about it in terms of this like energy release per unit mass of fuel, then in the burnup equation, we have the fission power, which is the P sub F. That's like the total amount of energy coming from our fission reactions. We have T sub F, which is the time at rated power. So like when you turn the reactor on, there's some time that it takes from when your like reactor is cold to when your reactor gets up to hot full power. There's also time that it takes to ramp down. There might be like outages because like you have to refuel your reactor from cycle to cycle. So the chronological calendar time is not the same as the reactor spins at its rated power. So in this equation, we differentiate between the time at rated power and the chronological time. Um, and those are related through the capacity factor, which is the thing that says what's the fraction of the chronological time that we're actually operating. And then the mass, it's the energy that we extract from the fuel. And we don't get energy from any carbon in the fuel. We don't get any energy from any oxygen in the fuel. I guess carbon in the reactor itself. Like if your reactor has stainless steel components and things like that, you're not getting any energy out of those atoms. You're only getting energy out of the uranium heavy metal atoms, or like maybe plutonium if you're talking about a MOX fuel reactor. So it's only the mass of heavy metal that's involved in this calculation, and then we can write that mass of heavy metal in terms of other things, but fundamentally the mass of heavy metal is what's here. Same thing with the time at rated power. We could write the time at rated power as the capacity factor times the chronological time, but it would be fundamentally, we would be the time there would be the time at rated power. And if we think about this kind of definition, and you think about the definition for fission power, that if you take the power density and you integrate over the whole volume of the reactor, that gives you the fission power. And so that's going to depend on the flux in your reactor, right? The power depends on the flux, and the flux depends on the position in the reactor. Like if you have a sphere, if you have a cube, if you have a cylinder, whatever fundamental shape you have, the maximum flux is always going to be in the center of that bare reactor. So if the flux is a maximum there, then your power density is a maximum there, and therefore the fuel is going to burn up faster where the flux is highest, which would be in the center. So that's where you have the maximum depletion is in the center, and then the depletion would be less everywhere else, assuming it's like a homogeneous material with the same enrichment everywhere. Um, Another related thing was the fluence. In that equation for burnup, if you write it, you'll get a product of a flux times a time interval that the reactor is operating. There's a related definition of the fluence, which is the time integrated neutron flux. So you take your neutron flux, you integrate it over some time interval, capital T. And the fluence basically tells you about a measure of like radiation damage because of the neutrons in your reactor. These neutrons, like reactors have a very high radiation field. So any materials that we put in our reactor get damaged by all of these high energy neutrons that are basically colliding with these materials as the fission reactions occur. And so in material science, there's like a thing called displacements per atom, which is like if you have some crystal lattice and you have individual atoms in that lattice, how many displacements do those individual atoms experience? Like if we have the pressure vessel or the reactor vessel of our reactor core, the atoms in that like stainless steel will actually get knocked out of their positions when neutrons interact with them, and over time these atoms get displaced in all these different all these atoms get displaced from their original place, and that causes damage to the reactor vessel, and after a certain point your vessel has to be swapped out. We care about fluence. If your flux is relatively constant, then you can pull the flux out of your time integral, and then the fluence could just look like a flux times a time if the flux is relatively constant in time. And then we started talking about from our production destruction equations, we started thinking about how we could express those kinds of equations for the buildup of the fission products that we care about, like specifically samarium and xenon. Um, Basically, these are like the two most important fission products because they have very large absorption cross sections. And so we can group most of our fission products together and have like a big group of pseudo fission products. And then we can deal with the samarium and the xenon kind of separately to kind of simplify how many nuclides we would have to keep track of in our core. So we talked about the way that samarium gets born in our reactor. Basically, it comes out of a fission. It's born from a fission product. So you have a fission reaction. Fissions produce neodymium with some yield. Neodymium is radioactive and it eventually decays into promethium, which eventually decays into samarium-149, which is the one that has the very large absorption cross-section. So samarium gets born from fission and then it's stable. So the only way that samarium leaves our reactor is if it absorbs a neutron and then becomes something else. So that's one of the things about samarium is that it doesn't go away unless we burn it up. So that makes it different than how we have to handle, say, xenon. Um, and basically from this decay chain, we simplified it a little bit. Like the decay of neodymium is so fast that we can assume that this fission just directly produces the promethium with the yield corresponding to the neodymium from fission. And we simplified this chain a little bit more to basically develop these um, conservation statements for the amount of promethium in our reactor and for the amount of samarium in our reactor. So these are fundamentally just differential equations that say how does the change rate of the density of these materials of the samarium and the promethium change based on the different ways that these nuclides are being gained in our reactor and the various ways that these nuclides are being lost. So fundamentally, that's all that these equations say is like change rate equals gain rate minus loss rate. And then from the decay chain, you can get a sense of like, for promethium, for example, it's being born because of fission, and then it's being lost because of radioactive decay. So the gain rate looks like a fission yield, and the loss rate for promethium looks like a decay loss. And then it's promethium that is decaying, so its decay loss looks like its lambda times its number density. And promethium is being gained because of fissions, and there's a fraction of those fissions that produce neodymium, which eventually produce the promethium. So our gain term for promethium looks like a fission rate density times the yield from of all of the fissions, what are the fraction of them that produce neodymium? That's what this yield term tells us about. And then we have a similar, we can do a similar thing with the samarium, right? The samarium gets born every time promethium decays. So the gain term for samarium is like a decay gain density, and it's the promethium that's decaying into the samarium. So the gain term for samarium looks like the lambda from promethium times the number density from promethium. And then the loss density, samarium gets lost in our reactor every time it absorbs a neutron. So this looks like a loss rate density for samarium, where it's the flux. And then this is effectively the macroscopic cross section for samarium, which is its number density times its microscopic absorption cross section. So these are like the fundamental equations for the concentrations of the promethium and the samarium in our reactor. If we know our initial conditions, then we can solve these equations to find out how these concentrations change with time. And so that's what we talked about. And we basically said we can solve these equations starting at the beginning of life when we assume that there's no fission products at the start of our time interval. And that's how these equations came about. And then we said, once we have these equations that tell us how the amount of these nuclides evolves with time, we're going to want to know, as time moves forward, how much of these nuclides do we have? Do they reach some maximum amount? Do they just grow forever without stopping? What's like the time behavior of these concentrations of these nuclides? And the way that we found that was by taking the limits as t goes to infinity of our solutions. And fundamentally, when you're taking the limits as t goes to infinity, you're kind of seeing what's the end behavior. And for both of these functions, the end behavior is that they both basically go to a constant value. If you take the limit of both of these functions as t goes to infinity, it means that and you see a constant value, what that means is that as time goes forward, they reach a steady state. And that means that their derivative with respect to time is zero once you've reached these concentrations. So part of the if I were to ask you to find these equilibrium concentrations, one way you could do it is you could go through and solve, these two original differential equations. You could solve them. You would have to do an integrating factor to solve the first one. You would have to do sorry, let me go back, because these are the differential equations that we solve to get these functions. So both of these differential equations would be solved using integrating factors, and these would be the results. And getting there would probably take like, I don't know, it would take me like at least an hour, maybe more to crank all that out. So like that's quite a bit of work to get these equations and then take the limit. But if I asked you to find the equilibrium concentrations, you don't actually have to solve the equation and take the limit. You could just set the derivatives in these two equations equal to zero, and that's going to correspond to the time when these things are at their maximum. So I just want you to notice that to get these equations, you could take the limits of these solutions as t goes to infinity, but you could also just set these two derivatives equal to zero and then solve for the amount of promethium at that corresponding t infinity, and also solve for the amount of samarium at that corresponding t infinity. Because like notice this first equation, if we set this equal to zero, and then we get promethium by itself, we're going to end up like adding this term to the other side. We're going to end up dividing by the decay constant. So the equilibrium amount of promethium would look like this term divided by the decay constant for promethium. And that's exactly what we saw for the amount of promethium at the equilibrium amount, because that's what it corresponds to. It's when time goes to infinity, but if these are reaching stable amounts, that corresponds to when the derivative is zero, which makes it a lot easier to find the concentrations this way versus having to solve two differential equations and then take the limit. So these equilibrium concentrations are important too, because it basically tells us after the reactor runs for a long time, this is how much of these two isotopes are going to be born in our reactor. And then we can ask the question, what happens when we shut down from there? And when we shut down, we're saying the flux is basically removed from our differential equations, and that changes the governing differential equations because any of those fission terms go away. And as a result, we can solve for new differential equations that describe the behavior of these concentrations after the shutdown. And what we will end up seeing if we take the limits of these equations is that both of if I take the limit of the promethium equation, it ends up going to zero. So what that means is that when we started up, the promethium got to some equilibrium amount, and then when we shut the reactor down, that amount exponentially decreases away. Eventually, the amount of promethium goes to zero. Whereas with samarium, when we shut off the reactor, the promethium that was there continues to decay, and the samarium that was originally there can't disappear if the flux is zero. So what happens with the samarium is that it slowly builds up to a newer, higher concentration that corresponds to the total of how much samarium I had before I shut down, plus the amount of promethium I had before I shut down, because basically all of that promethium that I had before shutdown decays into samarium. And once the samarium is there, the only way I can get rid of it is to turn the reactor back on. So that's essentially what this plot is showing. It's showing at startup. When I start up, I build up to this equilibrium concentration. When I shut the reactor down and my flux goes to zero, the amount of samarium continues to build up, and it builds up to the point where the amount here is the samarium equilibrium amount plus the promethium equilibrium amount. And then the only way to get my samarium out of the reactor is to turn the reactor on to make fission start to happen so that those samarium atoms can absorb neutrons and become something else. So when we turn the reactor back on, there's no more promethium to decay into samarium. So when we turn that reactor back on, all of the samarium immediately starts getting burned up, and there's no way for it to be replenished until these fission reactions have time to produce more promethium, which will eventually produce more samarium. So that's why we get a sharp drop as the samarium is getting burned up, but then eventually after a couple hundred hours, the promethium starts to build that back up, which starts to build the samarium back up, and eventually we come to a new equilibrium concentration of the samarium in our reactor. So this is a plot that we want to be familiar with. I wouldn't ask you to solve those differential equations because they take too much time, but you can kind of get around solving them by just setting the derivatives equal to zero to find these equilibrium concentrations. And then, yeah, being familiar with this graph would be good too. And so that explains kind of what happens with the samarium in our reactor. And something to recognize is that the buildup of samarium depends on how much promethium is there, and how much promethium is there depends on the flux in the reactor, right? If I go back to the equilibrium concentration for promethium, it depends on the flux. So if my reactor is operating at a higher power level, therefore at a higher flux level, I'm going to build up more promethium, which will then in turn build up more samarium once I shut the reactor down. So if I were to look at, we can think of the samarium concentration as adding negative reactivity to our system. So that's what this plot is showing. It's showing the negative reactivity of the samarium after as a function of the time after shutdown. And it's showing that if the initial flux is higher, if the flux is higher, then we build up a larger concentration of samarium because the buildup of the samarium, again, depends on the buildup of promethium, which depends on the flux. So samarium is one important fission product we keep track of. Xenon is the other important one, and arguably xenon is actually more important because if we look at this plot, which is showing some cross sections, absorption cross sections for samarium and for xenon, and then total cross sections for the other nuclides that are likely to be in our reactor core. Um, Samarium is the like kind of dark blue one, and then xenon is like the orange one. So notice at basically any energy level in the thermal energy range from like 1 eV and lower, the absorption cross section for xenon is almost always bigger than the absorption cross section for samarium. And it's not just a little bit bigger, it's like at least, this is almost like 2 orders of magnitude bigger when we're talking about at these kind of lower energies. So xenon is actually like the most important fission product. At thermal energies, its cross section is actually it's xenon basically has I think the largest cross section of any nuclide. So the microscopic absorption cross section for xenon 135 at the thermal energy range is about 2.7 times 10 to the 6 barns. So xenon basically has like the biggest, I think it's the biggest cross section of any nuclide, at least that I'm aware of. Um, so the absorption cross section for xenon is huge. Its cross section is so much larger than anything else in our reactor that in terms of like a tug of war, like competition for if something sees a neutron, which thing is going to absorb that neutron most likely, it's xenon 135. Um, so xenon's another one that we got to keep track of because its absorption cross section is so large. Yeah, yeah, it's a gas, and so basically what happens is that when your fuel fissions, if it's like a fuel atom that's near the inside of the fuel, then you'll just end up with these fission product gases that build up in like the fuel matrix. Like like if it's a material, if it's like a ceramic, it's getting stuck somewhere in that like crystalline lattice. And whereas if it's on the outside of the fuel, then that xenon gas can basically build up inside that little gas gap in between like the fuel and the cladding. Um, so where does xenon come from? Xenon actually comes from two places. It comes from fission. So any time that we have fissions happening, the xenon can be produced directly from those fissions. Like it's a directly formed fission product. So if we have a type I fissionable nuclide that fissions by a neutron that's in group G, and that fission produces xenon 135, then we could talk about the yield associated with that formation of xenon. And so we would say that we have a yield to go from a I type fissionable nuclide to xenon 135. And this is going to be different for neutrons of various energy groups. So that's how we would denote the yield of xenon 135 from the fission of a type I nuclide caused by a neutron with an energy that's in group little g. Different neutrons might produce xenon at different rates. So you have a yield that corresponds to all these different neutron energies. And it basically says of all of the fissions that happen, what fraction of them produce a xenon, so that when I talk about the yield for xenon, I can write a fission rate density times that yield. And it'll basically say, this is how much of all of the fissions directly produce xenon from fission. And xenon also gets produced from the decay of iodine 135, which is another fission product. So, sorry, iodine it comes out of a fission. It comes from the decay of a fission product. So tellurium, Te, which is tellurium 135, gets born from fission. It has its own yield, which would be the Yi to the yield for tellurium 135. that tellurium is very radioactive. It basically instantly decays into xenon 135. Its half-life is only 19 seconds, so it's basically there and then it's gone. Um, the iodine gets born. The iodine also has like a relatively quick half-life of 6.6 hours, and then iodine will eventually decay into xenon too. So xenon has two production mechanisms. It gets produced directly from fission, and it gets produced from the decay of iodine 135. And then xenon is different from samarium in that xenon 135 is radioactive too. So once xenon is formed, it can be lost in the reactor in two different ways. It can be lost if it captures a neutron. It's got that very large absorption cross section, so it can absorb a neutron and transmute into something else. In the case of xenon 135, it transmutes into xenon 136, which has a much less significant absorption cross section. And then Xenon 135 also is radioactive. It has a half-life of about 9.1 hours, and then it will become cesium 135. So that's kind of like the life cycle for Xenon 135 in our reactor. And from this fission product chain, we could simplify this chain a little bit, and that's what we're going to do next. Um, so basically what we can say is that in terms of the decay of tellurium, this decay constant, this half-life is so short that we can basically say that the tellurium just directly produce that the tellurium directly produces the um basically that the tellurium almost is like not there. That we can say essentially the fission just directly produces the iodine, and then we can use the production from iodine. The fission production we can multiply by the tellurium yield to basically say of all the fissions that occur, they're going to produce this amount of tellurium, which is eventually all going to become iodine 135. And then we're going to say that the fission product chains ends when xenon gets destroyed. So that means that we're going to kind of ignore the formation of cesium and the formation of barium. So in that sense, what we want to do is develop some basically equations that to say how does the concentration of the iodine and the xenon change as a function of time. And these production destruction equations fundamentally they're just conservation statements. So like for the iodine 135, I'm going to say that the change of iodine with respect to time is equal to the gain rates from iodine minus the loss rates from iodine. And what we just want to be aware of is that when I write dn dt, what are the units of this dn dt term? What are the units of n? Yeah, it's a density, right? So it's like per cubic centimeter. Like atom, you could put atoms up here per cubic centimeter, but yeah, it's got per unit centimeter cubed units. And then the d by dt term, what kind of units are associated with that? Yeah, that gives me like a 1 over time. So fundamentally, the units of this term is like a rate density. It's like per unit volume and per unit time. So any gain terms need to look like a gain rate density, and any loss terms need to look like a loss rate density. And then so we can ask the question for iodine, how does the iodine, if we're thinking about gains and losses, how is the iodine being gained in the reactor? Yeah, perfect. It's getting born because of a fission yield. So I'm just going to write this conceptually. I'm just going to say fission yield. And then I like that we said from tellurium. I'm going to add that too. I'm going to write it as words, and then we'll fill in the equations next. So that's the only way that iodine gets born, right? Every time this tellurium fissions, it eventually is going to produce the iodine, and there's going to be some yield of the tellurium that corresponds to how much iodine is being formed every time a fission happens. And then how is iodine getting lost from the reactor? How about how does the iodine get lost? Iodine becomes xenon, and how does that happen? Yeah, it decays, right? So the loss is going to look like a decay. It's going to look like a decay loss um, of the thing that's decaying, right? Which is iodine. That's fundamentally, and I only have one gain, right? I only have one arrow going to my iodine, and I only have one arrow going away from my iodine. So I only have one gain and one loss. And so what is that fission yield gonna look like in terms of like an equation? So fundamentally the units here, it's going to be like a fission rate density, right? And then there's going to be a multiplier that's the yield of the tellurium. So what would like my fission rate density look like? Yeah, perfect. It's going to be a sigma F, and that sigma F is for the fuel, and then times the flux. That's my fission rate density. And then that gets multiplied by the yield of tellurium, which basically says of the total number of fissions per unit volume and per unit time, this is the fraction of those fissions that give me the tellurium that eventually becomes the iodine. So that's my fission yield from the tellurium. And then my decay loss, what's my decay loss term for iodine going to look like? It's like it's going to look like a lambda for that nuclide times the amount of that nuclide. So it's going to look like a lambda I times an ni. And so notice like if I think about the if I just think about the units of these terms, right? This term right here, it's a sigma f, so it has like units of inverse centimeters, times a flux, which has units of like 1/centimeters squared per second. So notice this first term, the yield is just a fraction, so it doesn't have any units associated with it. So this has units of a rate density. And similar thing with this lambda I times this ni. We're doing a lambda, which has units of inverse seconds, times a number density of iodine, which has units of inverse centimeters cubed. So notice that these also multiply to give me a rate density. So this is just me convincing us that these are the right forms of these terms because the units match up. And that part of the reason that I harp away on like units so much and being able to say like what's the term, what are the units, is that if you know that information, it's a very powerful check to make sure that like when you set up an equation, it's if the dimensions are right, it doesn't mean that the equations are right, but it is if the units are wrong, then it's a surefire way to mess things up. So the units are important, and so that's what it would look like. That's the equation that what would describe the amount, the differential equation that would describe how our iodine changes as a function of time. And we could do a very similar thing with the xenon. We're also going to want to talk about how the xenon concentration changes with time. And so for xenon, it has a lot more going on. Um, this is fundamentally going to say change rate of xenon equals all of the gain rates minus all of the loss rates. So what are the ways that xenon is being gained in our reactor? Decay of iodine, perfect. So we'll say decay gain from iodine. That's one gain term, and I'm going to say plus because we're going to have another gain term. And what's the second gain for xenon? Yeah, perfect. Xenon gets born from fission and it gets born from iodine decaying. So it's also going to basically have a fission yield. It has its own fission yield of the xenon because it's produced directly from fission. So those are my two gains, and it's going to be gain rate minus all of my loss rates. So I'm going to have a minus sign in front of every loss term. And what are the ways that xenon can be lost in the reactor? The xenon 135 specifically. Perfect, right? Yeah, this would basically just be an absorption. And so, yeah, that would be an absorption. We can say absorption loss. And then what's the other way that xenon can get lost? Decay, right? It can also beta decay into cesium 135. So we'll also just say decay loss of xenon. And so that's just conceptually the terms that we're going to have. And then we can replace these with their mathematical forms. So like, what would the decay gain from iodine look like? What would be like a formula I could use to talk about the decay gain from iodine? Perfect. Yeah. The every time iodine decays, it produces xenon. So the decay gain from iodine looks exactly like the decay, sorry, the decay gain for xenon from iodine is exactly just the opposite of the loss from iodine. It's just a lambda I times the Ni. Perfect. And then how about the fission yield of xenon? What's that going to look like? And what's the Y for? And the yield, yeah, this perfect. Yeah, exactly. So it's going to look just like this decay, this fission yield, but the yield is going to be for xenon instead of for tellurium. So we're going to have a sigma f times a phi times a yield of xenon. Perfect. And then we've got a loss, an absorption loss, and we've got a decay loss. So the absorption loss, remember, these are all reaction rate densities. So my absorption loss is going to look like an absorption rate density. And how would I write an absorption rate density? Perfect. Yeah. So it's going to be perfect. Yeah. Like this, the sigma F times the flux is my fission rate density. So a sigma A times the flux is going to be my absorption rate density. So like in general, we're saying a sigma times a phi is a reaction rate density. And so a sigma A times a phi is our absorption rate density. And then we can break out this is the sigma A in this equation, it's the sigma A for xenon 135. So we could write this as the microscopic absorption cross section for xenon times the number density of xenon times the flux. Just rewriting this product, the definition of the macroscopic cross section is that it's the micro cross section times the number density. So ultimately, we're trying to write an equation that describes the concentration of xenon in our reactor. So that's why we replace this absorption cross section with its definition so that we can write this in terms of the number density of xenon. So fundamentally, we're going to have a sigma A for xenon times a number density for xenon times a flux. That's going to be the absorption loss term. And there's a minus here. Let me put the minus sign actually in front of it. And then there's going to be another minus sign. And sorry that I kind of ran out of space here. The other minus sign is going to correspond to the decay loss from xenon too. Um, and the decay loss from xenon is going to look similar to the decay loss that we had from iodine. It's just that we're writing this equation for xenon. So the decay loss from xenon is going to look like its decay constant times its number density. So we would have a loss from decay of xenon that looks like the lambda for xenon times the number density of xenon. So these two equations, what we've done is that we took this simplified decay chain and then we developed conservation statements for the amount of iodine in the reactor and the amount of xenon in the reactor based on how each of these is being gained and how each of these is being lost. And once we've developed these equations, we could then go ahead and solve them for the amount of iodine as a function of time. Sorry, I say amount, it's a concentration of iodine as a function of time, as well as the concentration of xenon as a function of time. Um, so if we look at our equations, one thing to notice is that if we look at like the production from xenon, xenon gets produced both from the decay of iodine and also from itself being born from fission. Xenon also gets lost when it itself decays or absorbs a neutron. So if we look at the equation for xenon, it depends on the iodine concentration and it depends on the flux in the reactor because the flux is both producing xenon and losing xenon. It also depends on how much iodine is there because the iodine forms the xenon. So basically, if we think about that equation, we look at all of the production and losses, what we want to recognize is that how much xenon is there depends it depends on the atom density of the iodine 135 that's there. So it depends on the atom density of the iodine 135 at the time t. Whatever amount of iodine is there is going to impact how much xenon is there. So xenon gets produced when iodine decays. Oh, question?
Is this actual time? Is this the time I read power?
No, this is time. This is a variable. Yeah, it's just representing a time. Mhm. Um, and so yeah, and then xenon can also be produced from fission. The fission rate and also the absorption rate both depend on the flux. So it's going to depend on the iodine and the flux phi in the reactor. And in these derivations, we're going to assume that the flux is constant. So we assume why is it helpful for us to assume that the flux is constant? Like, what's that helping us simplify? Yeah, and the reason that we want it to be the same is that if the flux was changing, that's going to affect our fission reactions. That means that it's going to affect how much of these concentrations, like how much iodine and xenon are being formed, and also the formation of these things, like xenon adds negative reactivity to the system, which is further going to affect the flux. So if the flux is time dependent in these problems, we have very complicated coupling between the flux and the densities of all of these concentrations because the flux and the power, like if I want to calculate power, I need cross sections, and the cross sections depend on how many nuclides are there and in what amounts. So there's like complicated coupling between the flux and these densities that we can ignore if we just assume that the flux is constant over whatever time step that we're looking at. So if we say that we're looking at the beginning of life of our reactor fuel, like right when the fresh fuel starts to fission, if we let that initial time when we've turned the reactor on be t equals 0, then once in those startup beginning of fuel life conditions, we can assume that the amounts of the concentrations of these nuclides is about how much at the beginning? Yeah, at T naught equals 0, the amount of both of these concentrations it's reasonable to assume that it's 0 at the beginning of life. So the amount of xenon and the amount of iodine at this T naught of 0 is 0. So if we have our initial conditions that they're both 0, the concentrations are both 0 at time t not equals 0, then we can solve those differential equations that we just formed for the amount of iodine as a function of time and the amount of xenon as a function of time t after we've started the reactor up. And the way that you would solve both of these is by doing integrating factors. You would use an integrating factor to solve the first one. You would take this ni of t, you would plug it in here. Like once you knew ni of t, you would plug it in here, and then you could solve this second equation for the amount of x at t. So the solution for I goes into the solution for X, and that's partly why this X equation is so much more complicated. Um, and once you have these amounts and you know how these concentrations are evolving with time, we can ask the important question, which is like, how much of these things do I get at some time t after startup? Like if I let this reactor run for 200 hours or 300 hours, what are the concentrations of these fission products going to be? Are they going to decrease exponentially? Are they going to increase exponentially? If my xenon is increasing exponentially, I have a big problem with being able to make a reactor be critical for a long time. So that's the next thing that we would want to ask is how do these things build up with time? And so the way that we would do that is we would ask the question, what do these concentrations look like at some long time t after startup? In other words, if we're asking what do these things look like at a very long time, mathematically, what are we saying? What are we trying to look at? Yeah, we're basically looking at like the limit as t approaches infinity. So we're going to basically take both of those equations for iodine and for xenon, and we're going to take the limit as t goes to infinity, and then we're going to ask how much of those nuclides are there. As t approaches infinity, how much iodine am I going to have at infinity? And how much xenon am I going to have at infinity? That's what we want to figure out. And we can figure that out by just taking the limits of these two equations. So, like if I look at the iodine equation and I take the limit as t goes to infinity, the only place t appears is here. So if I let t go to infinity, what's going to happen to that term? Goes to zero, right? And nothing else has t in it. So as t goes to infinity, the amount of iodine is going to go to this quantity right here. It's going to look like a flux times a sigma fission times the yield of tellurium divided by the decay constant for the I nuclei. How about oh, this should be xenon. So that's what it looks like for iodine. For xenon, again, the only places I have t's are in these exponentials. So I have a t here, I have a t here, and I have a t here. All of those are negative exponentials, right? So if I let t go to infinity, all of those exponentials are all going to go to zero, right? So this goes to zero, then I just am left with this term right here. If these two go to zero, then that whole thing in the brackets is zero, which means this whole term gets knocked out from that limiting process. So ultimately, all that's going to be left is just this term right here. So we're going to have a flux times a sigma f times the quantity yield of tellurium plus the yield of xenon, all divided by the decay constant for xenon plus the flux times the sigma A for xenon. So notice, one thing to notice is that both of these concentrations depend on the flux, right? Both this and this are flux dependent. Um, that means that how high we're running our reactor, like what power level we're running the reactor at, is going to influence how much xenon gets built up. It's directly the amount of equilibrium xenon in my reactor is directly proportional to the flux that's in my reactor. I guess for xenon, it's a little bit more complicated than directly proportional because it appears in the numerator and the denominator. The iodine, it's directly proportional. For xenon, I guess it's a little bit more complicated, but it still does depend on the flux. And so this is one way that we can find these equilibrium concentrations is we can solve our equations. We can take the limits of those equations as t goes to infinity. If I wanted to find these results, what would be a way I could find these same results um, without having to maybe solve and take a limit? Perfect. That's exactly right. We want to know that we can find the same result by just setting the derivatives in the original ODEs to 0 at this t equals infinity. So it's kind of like you're evaluating the derivative, you're evaluating the differential equation at t equals infinity, and then you're saying the derivative at as t goes to infinity approaches 0. So then if you were to take this equation, for example, that we had for iodine, what we're saying is that we're setting the derivative equal to 0. At t infinity, this derivative goes to 0, and at t infinity, this ni becomes the amount of I at t infinity. And then if I wanted to find the amount of I at t infinity, I would just solve this equation where this is a 0. So I would like add this term over, and then I would divide out the lambda I, and then the amount of iodine that I have at that t infinity would look like that. And I could do, hopefully we could see a similar thing that if I were to take this second equation and I were to let this derivative go to 0 and I were to solve this equation for the amount of xenon, notice that here I would have, if I evaluated at t equals infinity, then the derivative is 0. This is the amount of I at infinity. This is the amount of xe at infinity. This is the amount of xe at infinity. And I know the amount of I at infinity was from the previous thing, so I could plug that in here. And then I would have an expression that I could use to solve for the equilibrium amount of xenon, and you would get, if you did that, you should get this right here. So that's another way that we can find those equilibrium concentrations. And that basically tells us if the reactor runs for a long time, this is how much of those fission products are going to be formed some long time, like a couple hundred hours after we started the reactor up. If we look at these equations, they are exponentials. And so if we look at these exponentials, what are the time constants that are involved in those exponential functions? So like, for example, the time constants, like if we were thinking about back to point kinetics, when we had like e to the omega t, that omega was the time constant. So like mathematically, if you have an exponential, the time constant is just the thing multiplying the time, right? So like this lambda 1 is a time constant. And also this lambda xe time plus the flux times the absorption cross section is another. And then we see those same two time constants here and here. So like one of these time constants is lambda I, and the other time constant is lambda xenon plus the flux times the microscopic absorption cross section of xenon. And so if we think about these as exponential functions, then we can ask the question, like, how long does it take them to reach their equilibriums? And it will depend on what those time constants are. Like if these time constants are very, very small, then you'll reach that equilibrium depending on the larger those time constants, the faster you would reach the equilibrium. And so the way that you would find like the time corresponding to those time constants is that you would it's like the period, which is the inverse of that time constant. So like if we do 1 over lambda I, that gives us like a time characteristic of this time constant, and that corresponds to about 0.1 hours if we use the typical values for the decay constant of iodine. So one of these time constants is on the order of about 0.1 hours. And then the other time constant, if I do 1 over the lambda for xenon plus the operating flux times the sigma A for xenon, that comes out to about 30 hours. So one of these time constants is on the order of about 0.1 hours. In other words, in about 0.1 hours, those exponentials are going to decay away by a factor of E. Whereas if after 30 hours, those functions will change by a factor of E. So in general, it's going to depend on it's going to be dominated. The time behavior is going to be dominated by which one has the largest time, the time associated, the largest time associated with these time constants, which is 30 hours. So it takes about 30 hours for the amount of xenon in the reactor. Once you start it up, it takes about 30 hours for the reactor to build up to its equilibrium amounts. Um, so from there, we know what happens at startup. The concentrations start at 0, and then they build up to these equilibrium amounts. And then we could ask the question from there, what happens if the reactor operated for a long amount of time and then we shut it down? How does the reactor, how does the concentration of these nuclides change after we shut the reactor down? So we're saying at some new time t naught is when we're shutting the reactor off. That means that at past the time t naught, the flux goes to 0. So if we were to think about these original differential equations, past the time t naught, the reactor is shut down. So if the reactor is shut down past the time t naught, what it means is that the flux goes to 0. So if I think about these governing differential equations that had terms that corresponded to fission production and fission production and absorption loss, those fees, any term that had a fee in it in those differential equations is going to go to 0 if we shut the reactor off. So this differential, this is going to go to 0. This term is going to go to 0, and that the term with the uh, phi and the sigma a is going to go to 0. So here we're going to be left with lambda I times ni. And then for xenon, we're still going to have that lambda I ni. And then we're going to have a minus lambda xenon n xenon. So once there's no flux, there's no production or losses associated with the flux. And then our conservation statements basically just look like decay chains, where it's saying I decays, so it just has a loss term. Xenon gets formed when iodine decays, but it also itself decays. So these would be like the new differential equations that would describe what happens after shutdown. And we're assuming that we were in equilibrium before shutdown. So that means that like at the start of this transient, the amount of iodine in our reactor is this amount, and the amount of xenon in our reactor is this amount, where I've written phi naught to correspond to the constant flux level that the reactor was operating at. So phi naught is after operating the reactor for a long time at this constant flux. So we don't want to confuse phi naught with phi. Phi naught told us basically how much of these products got built up while we got to equilibrium, and then this phi in our equations is saying the phi that governs our differential equations goes to 0, but the phi that governs our initial conditions is based on what happened before the transient, so that phi naught doesn't go to 0. So we have the same initial conditions that we just found. Those become the start of the amounts of these two quantities after as time t for time t after shutdown. And so these are our new equations, and the post-shutdown behavior would basically just say, if we were to look some long time t after we shut down, what happens to the amounts of these nuclides in our reactor? And notice that all of these terms, so for iodine, we have a negative exponential. For xenon, we have a negative exponential and a negative exponential. So if we ask the question, a long time t after shutdown, what happens to the amounts of these nuclides as t goes to infinity for both the xenon and the iodine? Both of these eventually go to 0. The amount of iodine will go to 0, and the amount of xenon will go to 0. So basically what that means is that once we've built up some equilibrium amount of xenon and iodine, if we shut the reactor down, eventually both of those xenons and iodines are going to just effectively decay away, right? They're both radioactive. They both have some characteristic half-life. If you wait long enough, the xenon will just decay out of the reactor, and you don't have to worry about like needing to, with samarium, to get the samarium away, you have to start the reactor up to burn up the samarium. With xenon, you don't have to do that. If you've got a lot of xenon in your reactor, you can just wait some time the xenon will decay, and then your reactor will be easier to start up again. So if we think about these governing differential equations, we're saying that as time gets very large, both of these quantities is going to go to zero, but that doesn't mean that in the interim that they both continuously decrease. Like if we think about the iodine, for example, iodine probably is going to continuously decrease because it has no way to be produced. Like you've got some amount initially, and then it's just exponentially decaying away. Whereas for xenon, it is being gained and it's being lost. So there's the potential that xenon could actually increase after shutdown before eventually decreasing, like asymptotically going to zero. So we kind of want to know, when does xenon increase after a shutdown? What characteristics of our reactor would have to be there for the xenon to increase after shutdown? So we know the equilibrium concentrations of both. And if we consider our xenon differential equation, if we were to evaluate it at the start of this transient at T naught, then basically what we're saying is that we're taking our equation and we're evaluating it at some time. So we're evaluating, we would have lambda I, which is a constant, times the amount of I at this time. And the time T naught, at time T naught, the amount that's there is equivalent to the amount that I had in my equilibrium state. So I'm just going to write infinity, and then I'm going to write lambda xenon times the amount of xenon, also evaluated at T naught, but at T naught, we had our equilibrium concentration of these nuclides, which we use the infinity for. And then we know what those equilibrium concentrations are. We already showed what it was for iodine and for xenon. So the next thing that we could do is just plug those definitions into here. So like for the equilibrium concentration of iodine was the initial flux times the sigma F times the yield of tellurium, all divided by the decay constant for iodine. This term in the brackets was the equilibrium amount of iodine that we just found. And then for the xenon, we have a decay constant for xenon times the equilibrium concentration of xenon, which we also just saw was a phi naught times a sigma F times a yield times a decay constant for xenon. Um, sorry, I'm mixing my terms up. Sorry, sigma F times the yield of tellurium plus the yield of xenon. That's in the numerator. And then in the denominator, it was the decay constant, the lambda xenon, plus the initial flux times the sigma A for xenon. So all I'm doing is just evaluating this differential equation with post-shutdown differential equation. So the flux terms in my differential equation, the phi without the subscript goes away. And then I'm saying I'm evaluating this at this start of this new transient. And at the start of this new transient, I had the equilibrium amount of my iodine and I had the equilibrium amount of my xenon. And I've already found out what those two amounts are. And I just replaced them with those definitions. And so what we can do then is we can take these two expressions, we can simplify, we can like combine the right side under a common denominator, and eventually we want to get to a form where we have a sigma F times a yield of tellurium, and then times this quantity right here. And it's going to be two fractions, like a fraction on top of a fraction. And so up top, I've got a phi naught minus this quantity, where in the top I have the yield of xenon times the decay constant of xenon. And then the bottom of this fraction, I have the yield of tellurium times the sigma A for xenon. That's what's in the numerator. And then in the denominator, I have 1 plus another fraction here. And the top of this fraction, I have the decay constant of xenon. And then I have the initial flux times the sigma A for xenon. So getting here is just algebra. It's just algebra going from here to there. And ultimately, what we're trying to do is manipulate this expression so that we can ask the question, what does the flux have to be for this derivative to be positive, right? And in this expression for this derivative at t naught, in the numerator, I basically have the flux minus this other quantity. So the value of the flux relative to that quantity is going to affect if my derivative here is positive or negative. And if my Xenon derivative is positive at t equals 0, that means that my Xenon amount is going to go up a little bit before eventually decreasing exponentially to 0. Whereas if my Xenon derivative is initially negative, then that means that I'm going to start decreasing and I'm just going to continuously decrease. I'm not going to like have a bump up before I start to go back down. And so if what the flux is bounded by is this other thing in the numerator. So what we want to recognize from this is that if this flux is greater than the quantity yield of xenon times the decay constant of xenon over the yield of tellurium times the sigma A for xenon, if the flux is bigger than this quantity right here, then this thing in the numerator will be positive, then the derivative will be positive, and then the amount of xenon would increase before it eventually shuts down. Whereas if the flux was less than that quantity, then the derivative would be negative, and then the amount of xenon would just exponentially decrease, and it wouldn't go up before it eventually goes away. So this is part of a homework. Part of the reason I'm not showing all the steps here is because this is one of your last homework problems for the Xenon stuff. Um, you're basically just filling out the steps to go from here to here, and then you're gonna want to make this conclusion. Um, so hopefully that makes sense. And from there, we can basically we can think of the presence of xenon as also contributing some amount of negative reactivity to our system. So, and we saw that the amount of xenon there depends on the flux in our reactor. So this is showing how the amount of xenon after shutdown changes as a result of at different flux levels. So notice as the reactors are operating at a higher flux, you get a higher amount of xenon that gets formed. And yeah. And so part of the reason that we have this is that more flux means you produce more iodine. And then once you shut the reactor down, all of that iodine decays into xenon before the xenon itself eventually decays away. Question? Yeah. Mhm. Um, so notice like depending on what flux we have, the negative reactivity associated with our xenon gets higher and higher and higher. Um, there is a time constant that is associated with like how long does it take for our flux, how long does it take for our xenon post shutdown to build up to a maximum? We can see on this plot that for every flux, it's about 10 hours. A little past 10 hours is where the xenon amount peaks for these different reactors. And that effect is more prominent depending on the flux. Higher flux means you have a higher xenon peak. There's this line here that represents the maximum reserve reactivity. So like the concept there is that when our reactor is operating, the control rods are like partially inserted into the core. And if we were to take those control rods all the way out, we would be adding some amount of positive reactivity to the system if we were to remove all of the control rods at once. So that's like the reactivity, like excess maximum that we have. And the negative reactivity of xenon can be so large that it can basically dwarf the whatever our control rods could compensate for. So the negative reactivity from xenon can be more than the positive reactivity that our control rods could supply, such that your reactor would basically like have to be shut down. you would have so much negative reactivity from xenon that your reactor would basically have a dead time. And that dead time corresponds to basically how long you would have to wait for enough xenon to decay away so that the reactivity of the xenon was below the maximum reserve reactivity so that you would even be able to turn your reactor back on. Um, so that dead time is basically the time between how long it takes for the xenon to get back below that maximum reserve reactivity. And that dead time on here is about 40 to 50 hours. So this kind of shows, similar to how we showed a graph for the samarium, kind of what does the samarium do with time? This is what the xenon does with time. And at the beginning, it's the same. They both kind of reach this equilibrium amount after enough time has passed. Once you shut the reactor down, though, xenon will peak and then it will drop. And the reason that xenon peaks and then drops is that xenon is radioactive. So like with samarium, it is stable. So the samarium would just peak up and then level off until all the promethium decayed away. With xenon, it goes up and it goes down. It goes up because iodine is still decaying into xenon, but then eventually all of the iodine decays away, and then the xenon begins decaying away too. So you get a peak, then the xenon decreases as the xenon decays away. And once the xenon decays away, you might restart the reactor. And if you restart the reactor and you turn the flux back on, you kind of get a different behavior of the xenon, depending on if you just shut down and don't restart, or if you restart the reactor. If you shut down without restart, the xenon that's there just continually will decay away. And if you wait long enough, all of that xenon will eventually decay. If you restart the reactor, then the xenon actually drops faster than it does if you were to just shut the reactor down without restarting it. Um, why do y'all think that the xenon concentration is dropping faster on a full restart compared to just shutting it down and not turning the flux back on? Perfect, right? Xenon is being lost. Xenon can be lost both from decay and from absorption. So once you turn the reactor back on, once that flux is there, now neutrons can hit the xenon can absorb a neutron and become something else. So if you turn the reactor back on, you basically have two loss mechanisms. You have xenon being lost from it absorbing neutrons, and you have the xenon decaying away. And like eventually the reactor will fission, you'll build up more iodine, you'll build up more xenon. So when you turn the reactor on, it decreases, but eventually you build up the things that eventually build up xenon. Also, xenon itself will start to form from the fissions as well. So eventually when you turn the reactor back on, you'll come back to a new steady state that corresponds to the power that you were running your reactor at. So it has to do with the fact that xenon 135 experiences absorption loss and decay loss. And so yeah, that's why it drops so much right whenever you restart the reactor. It's like you have two loss terms versus one. So just like the samarium, we can think of the xenon being in our reactor as contributing some negative reactivity to the system. Um, just like we want to know, like, if our reactor is critical, it means K equals 1. But if it's critical when we start the reactor and then 10 hours after we run, or sorry, like once we turn the reactor on, we build up some xenon, which adds negative reactivity. If we were to shut the reactor down, we're gonna have more xenon forming. So like if the reactor is critical, we still have to compensate for the fact that xenon gets born as the reactor operates. So we need some way to account for the xenon being born by like maybe removing some of the control rods as the xenon forms, or reactors also have ways to do this in other ways, like there's dissolved boron in the coolant of pressurized water reactors, the boron is an absorber. So like when the fuel first comes in, you have a higher concentration of boron. Then as the reactor runs, as the fuel depletes, as fission products are born, you get negative reactivity from the fission products, so you can reduce the concentration of the boron in your reactor to kind of lower the reactivity, or sorry, add positive reactivity in different ways. So basically, the presence of xenon affects the reactivity of the system, and we need to be aware of how that's going to affect our reactor operation. Um, and so, um, yeah, and this is basically just this plot is kind of just reiterating what we saw in this region, where if you shut the reactor down and you still have a lot of iodine in there, then you need to be aware that all of that iodine is gonna decay into xenon, which is going to result in the xenon increasing before it eventually decreases. And so that formation of xenon can make a reactor harder to start back up, especially if you're not aware of how much xenon can actually add to the negative reactivity of your system. And so, yeah. This is just kind of illustrating how changes in the flux can influence both the iodine in the reactor and the xenon in the reactor. So we're showing the flux is like going from an initial value of phi0 to a lower value of phi1. So basically the flux level drops. When the flux level drops, the amount of iodine being produced drops too, because the amount of iodine there is directly proportional to the flux. And when the iodine decreases, and when the flux decreases, you get a jump in the xenon, because xenon gets formed from iodine, xenon gets formed from fission, but xenon also gets lost because it absorbs neutrons. So if you lower the flux, you're lowering like the absorption rate of xenon, and it's still being produced from the original iodine that was there decaying away. So you get like a bump in the xenon before it eventually settles back down. Um, and so, yeah, this is basically just showing how the amount of iodine and xenon would change as you decrease the power level of a reactor, and then as you turn the power level back up. And if you turn the power level back up to the original power, you'll have like a swing that results in things changing as a result of that power change, but ultimately things will level back off to the original, to the concentrations corresponding to those initial flux levels. Question?
What is that? I mean, they're that way.
It does to some extent, although these the feedback doesn't happen like in isolation, because like there are other feedback effects that will take place, but that is kind of part of the next slide, this thing of xenon oscillations. And so the idea here is that like if you have a very large reactor and you're moving the control rods in different places in the reactor, like maybe in one location you remove some of the control rods, in another location you insert some control rods. So like in the place where you remove the control rod, the flux is going to go up. As the flux goes up, you're going to have an increased burning of your xenon. The xenon going away means that you have positive reactivity being added. The positive reactivity increases the flux, which would increase the xenon burnup. So that itself, kind of like in the increased flux region, almost looks like we have positive feedbacks from the xenon. And then in the decreased flux region, it's in kind of another positive feedback where when you decrease the flux, you reduce you in the decreased flux, you still get xenon being produced from burning and from things decaying, but your flux is lower, and so you're going to get ultimately from those things the reactivity is going to decrease, which will further decrease the flux, further increase the xenon, and so these things are referred to as xenon oscillations, because basically in one place of the reactor you can have things like kind of going up, and you can have in another place things going down, and like eventually, because of other feedback effects like temperature feedback being the biggest one, it will kind of cause things will eventually settle out. but these oscillations can happen over pretty long periods, like 15 to 30 hours over which these things cycle. And like if you remove a control rod in a position in the reactor, it can take this amount of time, like 15 to 30 hours for those changes to like fully dissipate themselves in the system. And so it's kind of hard to monitor the xenon itself, but you can monitor other things in the reactor that would tell you if you might be having a xenon oscillation. And ultimately, monitoring that is really important because you don't want to have places in your reactor that are like very regularly like heating up and cooling down and heating up and cooling down, because that's really bad. Like things as things thermally expand and contract, there's like only so many times things can expand and contract before it starts to like damage the materials. So we try to avoid that in our reactors, and we monitor for the things that would indicate a xenon oscillation so that we can make sure our reactor components don't have like thermal stresses and shocks that are that we could engineer away. Um, so that was the last thing that I wanted to say about Xenon, and that was the last thing I wanted to say about chapter 8. So the last lecture, chapter 9, is the only new things I'm going to talk about. That's going to just be like kind of putting everything that we've done together lecture. So yeah, that should get us able to knock out the last homework 7 questions that involve Xenon. I almost worked through like an entire one of those problems with you. This one right here. So looking at this one will be helpful for that question involving this equality or inequality. And so yeah, if y'all end up with any questions on the, or if y'all have questions, or if you end up with questions about them, yeah.
Have we decided what the grading structure for the RDP is? Is that like necessary? Is that extra credit?
Yeah, it's going to be extra credit. So it'll be it'll add to a exam score, or it'll add to your quiz grade. So it'll add, I'll basically take the, like if the quiz was, or sorry, if the reactor design problem was out of like, if there was a percentage grade assigned to it, like 100% or 50% or 75%, that's going to translate to basically points. 10 points added to, 10 points maximum added to an exam. So like if you got 100 on the exam, then it would be 10 points on your, sorry, if you got 100 on the reactor design problem, it would be like 10 points on the exam. So it would add to your lowest exam score, or it would add to your quiz average, whichever would help your grade the most. Yes. 2 quizzes will still be dropped, and I'll do that once I have all of the quizzes entered. Yeah, I'll drop the lowest 2.
Where you couldn't start the reactor back up, how long is that, that like span of hours or minutes?
I guess it depends. Are we talking about from Xenon?
Yeah, on a typical like.
Yeah,
hour
it's like
reactor.
tens of hours. 10,
No,
20.
like the time in which it goes from you can start it back up because the xenon hasn't built up enough to you can't start up anymore. Right, because it's like 30 to 40 hours before you can restart it if you wait.
Yeah.
But because it like spikes, there's a point at which it reaches the level that you can't restart it. How long is that?
I see. I don't have that off the top of my head. Yeah.
Do you think it would be like minutes, hours, seconds?
If I had to guess, I would say probably like hours, but it kind of depends on the way that you could figure it out is by looking at those basically like the time constants that are in the governing equation. And so I guess that would also depend on like what kind of reactor you had. But yeah.
Just real quick,
Yeah.
so on the homework for the conceptual problems, we have to sketch a bunch of, I guess, graphs. It's
Yeah.
like K effective versus like time. Something.
Yeah.
I was just wondering like where I could find most of this.
So those are mostly just conceptual, like and I'm not looking for like anything. It's mostly qualitative too. Like generally, does it increase or generally does it decrease, or like does it increase and then it decreases? Yeah, nothing more complicated than that. And if you end up thinking about it and you want to like let me know how you're thinking, if you want feedback, let me know.
Okay.
Yeah.
Check for question with the burden
Mhm.
for that loss ratio. Given that possibility. And that's gonna be side, but for the.
No, be careful. So big M is the molar
Okay,
mass
that is the.
and the little m is the kilogram. So M oxide is the mass of the oxide.
So then for this part, is it just the ratio of percentage?
It's the ratios of the atomic masses in grams per mole.
So I want to talk about the 3%. So. So this is our 1,000. Then this is just, so we just put.
Yeah, so like if it was 100% 235,
Uh-huh.
the molar mass for the heavy metal would be 235 grams. And so if it's like 3% 235 and 97% 238, that is going to be basically 238, a little bit less. Yeah, and then the mass of the oxide would be just yeah, adding the oxide.
Okay, so it's just the. So then that's when we get these divide that and then multiply that by the actual kilograms.
Yeah,
to get
yeah, and then that
whatever.
in effect, that basically says of all of the atoms in there, what fraction of them are your heavy metal atoms?
You beat me to him, Sean?
Try it.
Smiling. Stern. That period you really stern. He's actually braided and then look at her.
That'd be a
I
good-
catch.
That'd be a good Halloween costume. Get a little peg leg.
When is he crying today?
Dang, let's say
I was the one, I was the sheriff's on the bus.
yeah, I got an email. Just over there.
Do I need, can I take a notes up to next class? On this? Do I need to have that? No. I do have to do it a lot of times.
No, I think you said it's fine.
And then, also during that time I submitted the last one, but, on my thing also, so it's like, where it's concerned with the work. This is like first week. It's like
Oh, so yeah, that's like a business thing.
So like weekends don't count as.
Um,
Cause like the,
Oh.
Friday and I submitted it on Sunday. So I'm just wondering how that.
sorry, yeah, I was yeah, so the weekends were count.
Okay. I think that's all so I can take it after.
Yeah, just let me know after class.
Okay, perfect, thank you.
I just wanted to ask, since the reactor was on extra credit, is that 10% that it was originally for on grade?
Just gonna go all to the homework.
Okay,
Mhm.
sounds good. Thank you.
I have a question.
Yeah.
For number number 4, what's MT national inversion concentration?
Oh, it doesn't have it, but it has capture. Oh, so if the nuclide fissions, it'll have a fission process. If it doesn't fission, it won't have a fission process, but it'll still have capture, and that's 102. So that's 102, and if I just to show you, I plot the total as well. This is for Xenon, and so at low energy, the absorption, the capture cross section is basically the total cross section, and at lower energies, I guess scattering probably becomes yeah. So at higher energies, it does more scattering than it does absorption, but at lower energies, which is the one that's for thermal energies, it's just basically a pure absorber. So yeah, you would just show. Sorry, I added extra stuff. You would just show one.
Oh. So, on the question, proportional singularity factor to divide into so I follow that online evaluation to enter a scale of the constant set.
Yes. Yeah, so the way that you find the constant of information is that you use the number. So it was kind of similar to like, I don't remember if you recall from like when we were doing like even just like with the decay differential equations where it's like
and that like, and equals negative lambda n, and so like, when you solve this, you end up getting like an n of t equals a constant times d negative lambda t. And it's a similar thing. The way that you find this constant is that you need some initial condition that would say like at time t equals 0, the amount is like, and then that is how you can find out that n naught is the so yeah, once you have this, you apply the initial condition and that output. That's it.